Hello everyone, welcome back to another video of an average programmer. Today I'm going to be solving the problem 1514 of LeetCode, which is path with maximum probability. I'm going to be using the same solving technique from my previous videos. This solving technique was introduced by Alex Nguyen in one of his videos. The title is How to Pass Coding Interviews Like Top 1%, and I'm going to leave the link to that video in the description box so you can check it out later. Okay, so he basically says that we need to split our process into three actions. The first one is plan, the second one is write, and the third stage is explain. So for the first stage, we're going to be discussing the problem, reading the problem, and also we want to understand the problem. Once we are done with this, we're going to think about some examples and also about some edge cases. Once everything is clarified, we're going to be thinking in an algorithm that could help us to solve the problem. So after that, we're going to pass to the next step, which is the write action. In here, we're going to be coding and we're going to put comments in each step, so it's easier for us to understand the problem, and also it's easier for the interviewer to understand our thinking process. And finally, we're going to get to the part of explaining our algorithm, and we're going to be also saying the time complexity of our solution. So let's get started. You're given an undirected weighted graph of n nodes. These n nodes are going to be zero indexed. This means that the first node is going to be the zero, represented by an edge list where edges in the position of I equals to an array of a, b. And this is going to be a tuple that represents an undirected edge connecting the nodes A and B. Okay, so these are going to be like our connections. And which is going to be the probability from passing from A to B. Okay, that is going to be obtained through this array. We're going to receive also the success probability, which is here, an array of number, and we're going to map the probability based on the index. And we're going to be given two nodes, start and end, and we need to find the maximum probability of success to go from start to end, and we need to return that probability. If there is not a path from start to end, we need to return 0. And your answer will be accepted if it differs from the correct answer by at most 1 times 10 to the minus 5 power. Okay, so let's see this first example. This is a really easy example to understand because here we only have 3 nodes, and here we have that our output is 0.25, which is like 25% of passing from 0 to 2. But if we see our graph, we can see that we have 2 paths. We can go from 0 to 1, or we can go from 0 to 2. But let's see which are going to be the probabilities. If we go from 0 to 1, we will have a 50% of probability of passing from 0 to 1. And then we will have also a 50% of probability of going from 1 to 2. So if we multiply these two numbers, we're going to get 0.25, which is bigger than going directly from 0 to 2. But I'm going to be showing you also other examples, and we're going to be solving them in right now. Okay, so let's see. We have our first example. We want to get from 0 to 5. So let's see our options. We can go from 0 to 2, or we can go from 0 to 1. So based on this, we have a higher probability if we go from 0 to 2, because we have a 0.5 probability, which is bigger than 0.3. So if we decide to do this, at this point we will have 0.5 of probability of passing from 0 to 2. And then we need to get to 3. Why to 3? Because from the node 3 is the only path that we can go to the end. Okay, so let's calculate that. If we want to get from 2 to 3, we will have to multiply 0.5 times 0.1, which is going to be 0.05. And here I'm using the theorem of probability of joint occurrence, which means this, that if we want to get the probability from getting from here to here, we will have to multiply these two numbers. Okay, so this by the first path. I'm going to put it in one color so it's easier for us. I'm going to put blue over here, and I'm going to put blue like this. Right? So now let's calculate the other path. If we go from 0 to 1, we will have a probability of traversing that path of 0.3. And then we need to multiply that to the other probability. In this case, is the probability of passing from 1 to 3. Right? So we will multiply that, 0.2. This is equals to 0.06. So we already see that the best path is going from 0 to 1 and then from 1 to 3. So at this point, it's easier for us to select a path because there is only one path that we can follow. 3 to 4 and 4 to 5. Okay, so let's keep doing that. At this point, we're going to be having a probability of success of 0.06 times 0.3 times 0.5. We have a probability of success of 0.009. So this is our answer. And this answer was constructed by traversing through these nodes, the yellow ones. Okay, so that's good for our first example. Now let's see our second example. Here we want to get from node 0 to node 4. So let's see our options. We have two options. We can go to 1, from 0 to 1, or from 0 to 2. And we have the same probability. So let's just select one randomly. We're going to be selecting this path from 0 to 1. Okay? So let's consider that. Now, if we want to get to 4, we will need to multiply 0.5 times 0.2, which is equals to 0.1. So we have a probability of success by this path of 10%, or 0.1. Now let's calculate the other probability. By the blue path, we have a probability of 0.12, which is higher than going from the yellow path. So we already found our answer. This is the answer, the blue path. Okay, so now let's see our edge cases. Here are our edge cases. So we want to get from 0 to 3, and we can see that we have the same probabilities from both paths. We can go from 0 to 1 and then from 1 to 3, which is great. And we can also go from 0 to 2, 0 to 2, and 2 to 3. We can see that the only thing that matters for us is the probability. So we do not need to output the array of the best path. So in this case, the answer is 0.03. Then let's see the other edge case. So we want to get from 0 to 0. And we can say that we have a 100% of probability of getting to the same node from any point, because we can implicitly say that we have a 1.0 probability of going from the same edge to the same edge. So in this case, the probability is going to be 1.0. And then let's see the last edge case. What would happen if we want to get from 0 to 2? Okay, so we can go over here, but we cannot get from 1 to 2. So in this case, we will need to return -1. Let's see if that's the... Oh no, 0. Sorry. That's my bad. So we will need to return 0. Perfect. So the only algorithm that could be useful for us is the Dijkstra algorithm. And I'm going to be telling you how we're going to apply this algorithm to this example. So let's go and see the solution. So here we are. In the Dijkstra algorithm, we will need to identify if we want to use a min heap or a max heap. And this is really useful for us to correctly use the algorithm. So that's the first part and the most important. And since we want to get the maximum probability, we will have to use a max heap. Okay? So that's clear for us. I'm going to be saying that this table is going to be the heap. Okay? So let's see our problem. And we will do the following. We will search first, or we will push the initial node. Why this? Because we will also want to consider the edge case for this example, right? So we will push the initial node and with a probability of success of 1.0. Okay, so we will pop that node, and once it's popped, we will expand it. Okay, so this is the representation of the expansion. This means that we will look for our neighbors. Here we have two neighbors, 2 and 1, and we will put that information into our heap. Here we saw that we selected the max heap, so our entries are going to be ordered in with a maximum parameter or with a max priority, and we need to identify based on which attribute we would like to order our heap. And we selected, for this case, probability, because we want to check first all the nodes that have the highest probabilities. Okay, so we will put our expansion result in our heap, and we have 2 and 1, and the heap is going to be ordering this information. So we will need to update the information of our heap. So we will multiplicate these values times our expanded node. Good? Okay, so we will do that. We will multiplicate 0.5 times 1 and we will get 0.5. If we multiplicate 0.3 times 1, we will have 0.3. Why 1? Because this is the expanded node, this one. Okay, so that's the first iteration. Now let's go to the other iteration. We will expand the node that is at the top of the heap. So we will have 2, right? So since 2 was considered to be expanded, we can see that our frequencies were expanding to the node 3. So we will put the node 3 into our heap. But what happens? The node 3 is at the bottom because it has a lower probability than 1. So we will multiplicate only the expanded or the neighbors nodes times the expanded node. So we will have that 3 is equals to 0.05. So we will pop the first element of our heap and we will expand it. The node that was popped was 1 with a probability of 0.3, right? So 1 was expanded and we see that we reach also node 3. You don't need to worry about the duplicated values in the heap because I'm going to be showing you what is going to be happening next. So since 1 was the expanded node, we will multiplicate only the 0.2 times our expanded node, which is 0.06. If you see, the other register was left the same because this is we didn't get to 3 from the last expanded path, which is this one. Okay, so we will pop the first one and we will keep expanding the node 3. We will expand this and we will get to node 4, and we will add node 4 to our heap. So now we will multiplicate only the neighbors 2 times the expanded node. So we will have that 4 was passed to the bottom because it has a lower probability than 3. So what would happen now? We will need to expand now 3, but 3 is really happy that it's going to be expanded, but we will see that he needs to be checked first if he was already in the expanded nodes. That is why I'm putting a box in each step. Every time that I'm expanding a node, I'm going to put that node into a box, which in this case is going to be a set in the code. So he is going to be left out and he will not get expanded. Why this? Because we already expanded 3. So this is a security method for us that is going to help you when you are creating the algorithm. So who's next? Who's next on the heap? Is 4. So we will expand 4. 4 is going to be expanded, and we have only 5 as the neighbor. We'll multiply 5 times node 4 and we'll get 0.09. And that's the answer. And that's how we get to expand the whole graph and get the maximum probability path. So now let's code that. So the first thing that I would like to make is to make the interface of the node. This is going to help us to have the idea of how the node is going to be looking like. Node is going to be an entity with a value and with a probability. Okay, so let's just declare that. Value and probability. Okay, so inside the main function, we need to create our variables. So the first variable that we will need to create is the adjacency matrix. But I would like to create the adjacency matrix in another function. So I will leave a space for the function of create adjacency matrix. We will also need a heap, and we also will need to make the initial push to our heap with the start node, and we will need to do some iteration. So we will have a while loop that it's going to stop when we don't have any registers in our heap, and that's what we saw in our board, that the algorithm ended when there were no elements in the heap. So while heap size is bigger than 0, we will do some iteration. Here it says iterate. Right, I'm missing something that it's really important for us, which is the visited set. This is going to be the box that is going to help us to avoid to expand expanded nodes. So this is going to be good for us, right? So we have the creation of our variables. We have the initial push to our heap. Help! to our heap, and we have an iteration of keep iterating while our heap has registers. So yeah, and we also need to consider to return 0 if we were not able to get the result from the while loop. So in this while loop, I will need to calculate the probability from start to end. So I think we have set up everything already. So I'm just going to pause and show you the solution. Okay, so this is the code. As you can see, we started creating the interface for our node. So we will have a value and a probability, and we will also have a function for creating our adjacency matrix, and we will receive the edges and the probabilities. And as we saw in the description, we will assign the probability based on the index. So we will declare a variable for the probability index that is going to be incrementing in each loop. And we're going to be making our adjacency matrix and return that adjacency matrix at the end. Good. So then we will have the variables declaration. We created our adjacency matrix, the visited nodes, and the max heap. And we made our initial insertion, which was with the start node. So we created the start node, and this was pushed to our max heap. So in TypeScript, we use the method in queue that is basically to push a register to the max heap, and we will repeat this operation while the max heap has a bigger size than 0. So what are we doing in each iteration? We are considering our expanded node, and we are popping the element from our max heap, and we will see if the value from the expanded node is the end node, we will return the probability. If it is not, we will do the following. If we have information, or if we have neighbors for that node, we're going to keep doing the algorithm. So we will, since we already passed through that node, we're going to be adding that node to the visited nodes, which is the representation of the box of the visited nodes. And here we're going to iterate through its neighbors, and we're going to get the values and the probabilities of its neighbors. So if we haven't visited that neighbor, we will put the new probability for that neighbor as the probability of that neighbor times the probability of the expanded node, which is this. And we will push that to our heap. So if we're not able to get the result with this loop, we will return 0, because that means that the node is not in the same graph. That the end node is not in the same graph as the start node. Okay, so this is the solution. Let me submit it for you to see that it's working. And the time complexity of this is going to be order of the edges plus vertices. Okay, so that is all. I hope it was useful for you. And yeah, see you in another video. Please do not forget to leave your feedback on the comments. It really helps me a lot to say what I can add to the videos, or what can explain better. And also I'm going to be working on my English, so it's better for you guys to understand me. And that's all. See you in another video. Bye.